This is really a great honor to introduce today's talk. Some of you might have noticed there's been a lot of talks about, other star systems and biology and so on. And that's completely deliberate on the part of Jacob Cohen's background. But also, I think it's really where the future is. As noted before, this is part of our 75th anniversary celebration. The colloquium series this summer is in honor of our 75th anniversary. But I am particularly pleased today to have Dr. Jill Tarter. She has devoted her career searching for evidence for sentient beings off Earth. There are others who have spent their whole life searching for them on Earth. Most of them failed. But in all seriousness, that she has changed our way of thinking about this. Her astronomical work is illustrated in Carl Sagan's novel Contact and the film version Contact. And we understand that Jodie Foster character was largely inspired by Jill, so I think she's much cooler. Jill is. Yeah, that's right. Asteroid 74824 Tarter, 1999 TJ16, has been named in her honor. Now, I have to say a story about it. Somebody wanted to name an asteroid after me. And they submitted it. And I was a general in the Air Force at the time and said, well, it turns out that the International Astronomical Union won't allow things being named after military figures or political figures. And not being a political figure, they used the military figure. So they named it after my wife. When I told her about it, she said, I'm sure that'll be the one that destroys the Earth. So. But Jill holds the Bernard M. Oliver Chair for SETI at the SETI Institute in Mountain View, just down the road here. And she serves on the Board of Trustees. We collaborate here at Ames very closely with Sophia, and they have been the principal partner in the science analyses and team for Sophia and Kepler. So really, really proud of having that. In 2004, Time magazine named her as one of the 100 most influential people in the world. Pretty cool, huh? And in 2012 was one of the 25 most influential people in space. She has a Bachelor of Engineering degree in physics from Cornell University, and I understand she was the only woman among a class of 300 engineering students, so congratulations. I hope that's much better now than... and a PhD in astronomy from the University of California at Berkeley. Her talk today is entitled Searching for ET, an Investment in Our Long Future. Jill, welcome back.
Well, Pete, I think you know how much of a pleasure it is for me to be back here, since this was my first job as a postdoc, was at NASA Ames, and we were working on brown dwarfs back then. They've been found. Yep. ET is yet to happen. So I think many of you may think, when you hear the word SETI, you may think, oh, that's fringe. You'll laugh to yourselves about little green men and flying saucers, UFOs. But in fact, I'm going to try today to convince you that SETI, the search, and all the work that gets done here at Ames, searching for other kinds of life, is incredibly important to our future, because these topics allow us to change perspective. They allow us to think about things and to see ourselves in a way that is not often used by the general public. But I think it's something that we need to share with them, because being able to step back, take this cosmic, larger picture view, is what we need to do in order to solve all of the challenges that face the planet and all life on it. And so I hope that I can change your point of view, and I hope that you'll get interested in participating in these grand searches. So this whole story, sort of your story, my story, our story, began billions of years ago, right? That's no secret to anyone who's taken a university astronomy course or anyone who's worked around this facility. But it probably doesn't come first to your mind when you wake up in the morning. You need to change that. All right? So our universe began in an enormous expansion about 3.8 billion years ago. And our Milky Way galaxy was born about 10 billion years ago. And we are intimately connected with these faraway times and faraway places, because it takes a cosmos to make a human. Humans can trace their lineage not just back through the centuries of our own families, not just back through the millennia of our civilizations with its buildings, its art, and its experiments with different forms of governance. We trace our heritage not just back to the millions of years since we emerged, branched away from the apes, not just back the 2.4 billion years during which Earth's atmosphere has been perfused with oxygen thanks to the ceaseless efforts of photosynthetic cyanobacteria, not just back to the formation of the sun and the solar system about 5 billion years ago, but all the way back to the supernova explosion and death of a massive star. The iron atoms in the hemoglobin molecules in your blood, the calcium atoms in your bones, were fused deep within a massive star that ended its life in a catastrophic convulsion, leaving behind remnants such as this more modern example, remnants that are now waiting to be incorporated into future generations of stars and planets and perhaps life. So it's taken millennia for humans to piece together the story thus far. And we're continuing on this journey, driven by our curiosity and our desire to understand, to know our place in the universe. We want to know, where did we come from? Where are we going? What is? Why is? And of course, we're really interested in whether or not there's anyone else out there. So far, the numbers suggest a universe of possibilities. Well, this clicker is a little bit jet-lagged. Okay. So let's do it this way. And right now, we're able to comprehend ourselves as living on a very fragile island of life within this universe of possibilities. We're just beginning to appreciate the possibilities here on Earth, the possibilities for our future, and those possibilities require embracing this cosmic perspective. So, extremophiles, something that many of you here are familiar with. This life that we didn't even know about until a few decades ago, thriving in places that we once thought were completely inhospitable to life. And these organisms are now illuminating the potential for life elsewhere and the possibility for a lot more habitable cosmic real estate out there than we once might have thought. So, an appreciation of life's incredible diversity and its scale is really the first step in contemplating the universe beyond our own cosmic doorstep. It's important to remember that we are not the pinnacle or the ultimate design of evolution. We're not the intentional product of 4 billion years of plotting and planning. We're simply a part of today's snapshot of a perpetually transitional form. So as we pry open those cosmic doors, we're testing these possibilities. And this amazing image, right, absolutely mind-blowing image, is thanks to the Curiosity Science Laboratory on Mars. Well, Curiosity wasn't designed to find life, but it's showing us that the conditions that we think are necessary for life did exist on this planet once, and perhaps they still exist in places today, buried beneath the surface of this frozen desert. Alternately, life may be found farther out in the solar system, in the water oceans beneath the ice of Europa, Callisto, Ganymede, right? These large moons of Jupiter. Or maybe in the ethane lakes on the surface of Saturn's large moon Titan. Or even perhaps on a tiny little moon Enceladus with its amazing cryovolcanoes. And these places are places that we or our surrogates may visit in the future and may be able to interrogate, looking for life. But it also may be the case that we have to look farther beyond our own solar system. And until 1995, we actually didn't know whether there were any planets around solar-type normal stars. But since March of 2009, the Kepler spacecraft, with which this facility is so heavily involved and so responsible for its success, Kepler's been following behind the Earth in its orbit around the Sun. And its mission is to tell us how frequently planets the size of the Earth actually form around other stars. So Kepler has a 93 megapixel camera, CCD camera, real high-end version of what you have in your phones. And it stares continuously at 100 square degrees on the sky. And it's in the direction that's just a bit north of the plane of the Milky Way galaxy because there are a lot of stars in that direction, and yet not too many. So Kepler's instrumentation doesn't get confused. So Kepler's staring at that patch of sky, which is like the size of your hand, and it's waiting for some of those 170,000 stars that it's concentrating on to blink. Or at least that's what it did between 2009 and 2013, my mistake. And as it turns out, many of them did blink. And this transit method, looking for a planet to pass in front of a star and dim its lights for a few hours, dim its brightness for a few hours, is extraordinarily successful. So today, on the Kepler MAST site, I looked up and there are 4,234 candidate exoplanets. That goes up and sometimes it goes down a little. And 978 of them have been confirmed either by other ground-based observatories and other methodology or statistically using the Kepler data themselves. And it turns out that because we have this chauvinism in our search for life, we think liquid water is really important. Then there are a few of these stars that appear to have planets in orbit around them at just the right distance, so that if there were an atmosphere surrounding that planet, it would be not too hot, not too cold, and might be able to support liquid water on its surface. And so we think a lot about this habitable zone. And I heard a really nice talk at the SETI Institute a couple of weeks ago, where my colleague Stephen Kane reminded us that we have to be careful here. We astronomers are going into hype land, right? We are talking about habitable zones, then potentially habitable planets. Habitable planets. You know, we really don't know. We know perhaps that the planet is Earth size. We know its distance from the star is potentially propitious. Sometimes we know its density, and we can say perhaps there's a rocky world there. But it's going to be quite a while. A disappointingly long time, I'm afraid, before we can say for certain what a habitable planet looks like and how many of them there are in the Milky Way galaxy. Nevertheless, hype alert having been given, right, we start to codify things. Of the things that we can remotely sense about planets around other stars, we try and compare them with Earth. And the first two in the list there have about 83% of their characteristics comparable to what we would measure on Earth, and who knows? Maybe 83% is good enough. Maybe not. You know, we actually don't even know what's absolutely necessary about the Earth for there to be life here. So this is a game that intrigues the public, invites the public into our discussions, and that's all good, but we have to be sure we don't overpromise. Now, I've said it's going to take a long time. I bet you Pete's going to beat me. I think that he might have something up his sleeve that could help us in this quest in a nearer term rather than a farther term, if we get lucky. All right, but recently at the SETI Institute, we were really pleased when Lisa Quintano and her colleagues announced the discovery of this particular planet, Kepler 186, the Kepler 186 system. And the fifth planet, 186F, happens to lie in the habitable zone that surrounds the small star, Kepler 186a. And it's much closer to the sun than the Earth is, because the star is much fainter. But this is looking like a very interesting target and one that we should continue to study. You know, we have a problem as we do this research when we really have only an example of one. And before we started making these discoveries, we would make models of what other planetary systems were going to be like. And it was really strange, you know? Every time we made a model, we produced all these planets, and they were all going around in nice circular clockwork orbits, and they're all in a plane, and the little rocky guys were on the inside, big gas giants way outside, just like us. And so it was an amazing wake-up call when we detected the first exoplanet around 51 Peg. It was bigger than Jupiter and in an orbit so close to its star that it went around in 4.3 days. That really was an eye-opener. You know, if you only have an example of one, your models are probably going to be pretty biased and not very reliable. But now, thanks to the Kepler, we actually have hundreds of multi-planet systems. And we can study the dynamics of those. And some of them are big guys on the inside, little guys on the outside. Some of them are circular, some of them are elliptical. We think some of these planets early in the history of formation actually get thrown out of their planetary system. But the fact is, now that we have many examples, we can begin to tease out and differentiate between what is necessary and what is contingent. And we'd love to have that possibility for biology as well. So when it comes to life, we still got just this one example. And so we've really got to be careful and not overly limit our thinking about what might be possible, or constrain the possibilities by saying it must be this. We have to remember that Homo sapiens is just one single leaf on a very expansive tree of life. And that tree is really densely packed with organisms that have been finely tuned over millions of years to meet their specific survival needs. And although, we know that scientifically, I think a lot of our fellow inhabitants of the planet certainly haven't internalized this idea. And our egos haven't yet caught up to this scientific understanding. We still have a tendency to say things like the ascent of man, pinnacle of evolution. All right, the second time I've gotten on this hobby horse, so I really am adamant about its being important, that this is a point of view, a perspective that the natural universe does not share. So get over it. All right? And as we think about these potential habitable worlds, or in my case, inhabitants elsewhere, we also really need to rethink what we mean about here and now. So, simple, right? We're here, right? Building 200, auditorium, and we're all familiar with Google Earth, and that makes us comfortable with conceiving ourselves as being here. And if you were at the altitude of low Earth orbit remote sensing satellites, you would see us here. Since Bill Anders took this picture in 1968 coming around the limb of the moon, we've appreciated ourselves here as an island universe. Cassini, the spacecraft, turned around from Saturn and took a picture of us here. There is a little dot under that arrow. That's where we are. And of course, in 1980, the Voyager 1 spacecraft, as it was leaving the solar system, starting on its journey outwards, it turned around and took this pale blue dot picture and showed us that we were here, embedded in the zodiacal dust of the solar system. And our star is here, right, out in the boondocks of Spiral Galaxy. We're only one of 100 billion or so, 200 billion, 300 billion, 400 billion, astronomical accuracy. Stars in the galaxy, and that galaxy is only one of 100 billion galaxies in the observable universe. So that's our context for here. But as we look at this image from the Hubble Deep Field, we're reminded that looking farther out in space is looking backwards in time. And so we also have to think about now in this larger context. Where are we? What's the future of the solar system, the future of the galaxy, and what about us? What's our future? And it's built upon this very deep past. So, in fact, we are the living and breathing products of about 1 billion years lineage of wandering stardust. I mean, we're what happens when a primordial mixture of hydrogen and helium evolves for so long that it can begin to ask where it came from. So we are stardust, and that's the reason there might be others out there as well. So in this context, it really makes sense to ask, is it really just us, right? And to crib a line from a pretty good science fiction movie about 15 years ago, if we're all there is, it seems like an awful waste of space. But nevertheless, that could be the answer. We don't yet know. Let's assume that perhaps we're not alone. What if somebody out there is asking and answering the same kinds of questions that we're posing here. Somebody that looks up at the night sky sees the same stars, but just from the opposite side. Might the discovery of an older cosmic culture inspire us to find a way to survive our increasingly uncertain technological adolescence? I think that's what SETI's good for. 50 years ago, our human journey to find answers to questions started down a new path, and the exploratory science that we call SETI, the search for extraterrestrial intelligence. I don't think anybody, or I hadn't thought to define it until just now, SETI, the search for extraterrestrial intelligence. We began using radio telescopes, leftover tools from World War II, and then at the beginning of the 21st century, we began to use optical telescopes. And what we're looking for is signs of someone else's technology. So we take a very pragmatic point of view. We can't define intelligence any better than anyone else can. But what we're using is a proxy for intelligence. We're looking for technology, something that changes its environment in ways that can be sensed over interstellar distances, right? And we use the tools of the astronomers to search for this evidence. Our own technology is detectable over interstellar distances, and theirs might be as well, even if we can't conceive of the reason for the construction of that technology. Even if we can't figure out why it's being sent, a determined program of searching might, in fact, discover it. And in fact, while technologies change, right, the physics of the universe, not so much, right? We don't think that the physics of the universe is changing, at least very quickly. Things do seem to have been fairly stable over tens of billions of years. But signals carrying information between the stars, they have to propagate through the interstellar medium. And understanding the physics of the interstellar medium, that means that it will constrain any engineers, ours or theirs, about the kinds of signals that propagate well through that medium. So we go looking for narrowband radio signals because they travel across the interstellar medium almost unchanged, and nature can't produce this kind of signal. Technology can. We go looking for very short nanosecond bursts of light, again because nature doesn't seem to do that in ways that are detectable over large distances, but technology can. And in fact, we may be looking exquisitely in exactly the wrong ways. We may not yet have invented the right technology for this job. So we do reserve the right to get smarter. And if somebody invents zeta rays a few decades, centuries from now, and they are the obvious answer to interstellar communication, well then, we'll start looking for zeta rays as well as everything else. It's just, I'm doing a little digression here simply to say that you do what you can. You try and push what you can into new areas, but there's really not a lot you can do about what you can't conceive, except stick around, survive long enough until you figure it out too. So whether or not SETI succeeds is going to depend on longevity. Right? It's going to depend on the distance between any two technological civilizations. And that's not just distance in space, that the technologies are close enough to detect one another, but distance in time. The two technological civilizations have to line up in this 10 billion year history of our galaxy to be coeval, so a message that's sent can be received. And unless technologies are long-lived, that's not going to happen. So Phil Morrison, one of the co-authors of the first scientific paper on SETI, had a lovely way of expressing that. He refers to SETI as the archaeology of our future. Right? Any information we get will have traveled between the stars a long distance, so it's really archaeology because it's telling us about their past. But if we were to detect a signal, wow, we know that it's possible to become an old technology. We know that it's possible to have a long future. And I don't expect cosmic salvation. I don't expect them to tell us how to solve our problems. But merely the fact that another advanced technological civilization exists should motivate us to figure out a way to solve our own problems. And in the 50 years plus that we've been doing SETI, our tools haven't been optimal. We've been using the tools of the astronomer. And if you take the 9-dimensional space that you might have to search through for different kinds of electromagnetic signals, assuming electromagnetic signals is the right thing to search for, you'd conclude that if that 9-dimensional volume was equal to the volume of the Earth's oceans, so far in 50 years we've sampled an 8-ounce glass of that ocean. And that's discouraging. We haven't sampled very much, but we haven't sampled very much, so we shouldn't draw negative conclusions. And the important thing to understand is that we are in an era of exponentially improving technology. This is going to get better. We're going to be able to search more. We're going to be able to search faster right now and continuing into the next decades. So I brought along, they wanted a prop, so I brought along a 1/8 scale model of the Allen Telescope Array in Northern California. Right? And it doesn't look like your father's radio telescope or your mother's radio telescope. It's pretty weird looking. Very innovative. And if you can see, there is a copper-colored pyramid down there. Right? That is this. This is a log periodic frequency-independent feed. It collects all radio waves from 0.5 gigahertz to 10 gigahertz. Right? When the size of the pennants are kind of like a dipole at 1/2 a wavelength, then this antenna gets excited. It's like the aerial of your car. Excite these pennants, a current flows along the backbone up to the top, a little circuit board, it turns it around, puts it right down into there. Voila, you're in a cryogenic dewar. From there to there. So 2 low noise amplifiers are kept at 70 Kelvin in that dewar. 2 senses of polarization, this sense and this sense. They're amplified and they come out on coax cables at the back. They're amplified again, they go to a control room and they're processed. We keep that dewar cold with a refrigerator that sits right inside there. So this is our entire feed and receiver cabin, and it's on each antenna, and it works amazingly well. However, we're getting more noise than we thought we would get. So that system is going to be replaced, and we're in the process of replacing it with this system. It won't go to as low a frequency. We've essentially cut it in half so that we could fit it into a glass bottle, evacuate the bottle, and cool the whole thing down, including all those little dipole fins. And now, at a colder temperature, we reduce the ohmic losses, and we improve our system temperature by a factor of 2 over the frequencies that we're currently working at. That's like building twice as many antennas. That's pretty cool. And we also made the tip even smaller, so we go up to a higher frequency. So this is only one of the instrumental improvements that are being made and that can be used for SETI and are being driven and being enabled by fast available computational capabilities. So it works really well, these feeds. And when we look at the planet Mars, this is sometimes the way it looks like. And so I'm plotting frequency on the horizontal axis, time on the vertical axis. For every target that we look at 9 billion 1 hertz frequency channels. I don't have to tell you a lot about that slide. You can intuit that all that snow is noise, and those bright lines are signal. And indeed, that's what this is. And when we looked at Mars on this occasion, both Mars Reconnaissance Orbiter and Mars Express were on our side of Mars, and we could catch their carriers that were being beamed back to the DSN. So this works at Mars, and it works at the edge of the solar system. So same graph, right? Just gonna let you stare at it for a while. There's a signal in there. It's coming from a lot farther away than Mars. So particularly to your eye, it's a lot fainter. On the other hand, there it is. And to our special purpose algorithms, there it is. Our computers can find these signals much, much better than we can ourselves. If you're interested in figuring out what we're doing on any particular day, John Richards at the SETI Institute has put up this really neat set of pages on setiquest.info. The one on the left, see, that's Inspector Clouseau, who's actually tapping his fingers because he's waiting for the observing to start. And when the observing starts, there is this buxom young woman with binoculars looking at the sky, right? I was a little leery about that, but you know, John was doing this, he's doing a great job, and it's kind of hard to, some creative license has to be allowed in the process. And the other picture is our progress to date. So what we're doing is looking at exoplanet systems, either found by Kepler or by ground-based systems doing radial velocity or microlensing studies. And you can see the big concentration of the Kepler candidates on the sky, and the other exoplanets are scattered around the sky. And we look at them 3 at a time. There are a lot of good reasons for that, but one of them is to help us exclude our own terrestrial signals. And it's a big project. We've probably got another couple of years of observing until we systematically have gone through all of the Kepler exoplanet candidates. But we might not finish that. In fact, Kepler has been so good that it's basically telling us that all stars have planets. And so my colleagues are now discussing whether to jump on the bandwagon and let's just concentrate on the nearby stars. Signals will be easier to detect for a given transmitter power. If we find them, there might be some more relevance to having them close by. So we'll either finish this Kepler project and then see what TESS has provided us, or we'll begin now with known planets, known stars that are nearby. But we are observing at least 12 hours of every day with the Allen Telescope Array. And if you happen to have an iPhone and you have the distant suns application on it, and you click on the little green radio telescope icon, you can actually see, well, not so well up there, but you can actually see the places on the sky that we are observing when you're looking with your iPhone. So we're trying to open this up and let the public experience what we're doing and be part of it. But we've tried a couple of experiments on citizen science projects, and we learned a lesson the hard way. We are a very small team, and when you try and invite the world in to help you, the world needs a lot of help. So we haven't found the right scale of citizen science project yet, which doesn't overwhelm our team in just the support for the citizen scientists. We're still working on it. There has to be, this is a sexy project, there has to be a really good solution. 10 years ago, the folks at Berkeley came up with a good solution called SETI at Home, where you could donate the unused CPU cycles of your home computer to look through recorded data. And that's continued to be a great idea, and many, many people have downloaded this screensaver. And this has sort of been a kickoff for distributed computing and citizen science around the world. It's a great idea. However, it's kind of install and forget, right? We'd like to find an application that engages people all the time, has them actively thinking about SETI while they're using whatever the application is. Because remember, it's my job to change your point of view. I can't do that if you're not thinking about things. So we want to find the right tool to keep people actively engaged. So UC Berkeley records data from Arecibo and does a number of different types of searches on that Arecibo data. They've also developed a wideband recorder at the GBT, the Green Bank Radio Telescope in West Virginia, the NRAO telescope, and they do occasional SETI observing there. LOFAR is a very low-frequency telescope that's spread across Europe and the Netherlands. That's beginning to do SETI. There's a group in Italy who's very, very keen. They're using this 64-meter telescope at Medicina to do SETI. Down at JPL, which was historically part of the NASA SETI program, they've had to wait until they could figure out a way to enable a sky survey on a telescope that's outside the fence. So the Gavert Apple Valley Radio Telescope, which is an educational facility, is now hosting a sky survey that the students are conducting. And in Japan, a gentleman has tried to organize the world's SETI observers in what he calls Project Dorothy. Dorothy is Dorothy as in Oz, right? This began as a tribute to the 50th anniversary of Frank Drake's Project Ozma. And occasionally around the world, optical and radio telescopes look at the same set of targets simultaneously. So this is the radio spectrum of SETI. And we are also now, since the beginning of the 21st century, doing optical SETI, which is not looking for narrowband compression and frequency, but looking for compression in time, looking for bright flashes of light that last a nanosecond or less. We don't think that nature can produce strong enough emissions in that coherent fashion, but lasers certainly can. Lasers focused by large telescopes can do even better. And so this is looking for someone else's laser signals. That's Shelley Wright in the middle with an instrument on Lick that she built as a senior undergraduate program thesis. On the left are two students of Paul Horowitz from Harvard who built their own optical sky survey telescope in Harvard. And on the right is a small telescope just outside of Sydney in Campbelltown that's used for optical SETI. Now the problem with optical SETI is that it gets blocked by dust and scattered in its transfer between the stars. So you'd like to move optical SETI down into the infrared, and technology is now becoming available to do that. There's an interferometer that Charlie Towns has on Mount Wilson that's being instrumented by the Berkeley group to do infrared SETI. That's Shelley Wright again, no longer a senior undergraduate, but a professor at the University of Toronto, who is beginning to build a new optical IR SETI detector using new diode technologies. And hopefully it will go on Lick. Down on the left, we see the Colossus, a concept of Jeff Koons, saying, look, the one thing we can say about an advanced technology is they have a need for power. They're going to process, and they are going to have waste heat from that use of power. So we'll build a huge telescope that can detect the waste heat, such as the back of this Dyson sphere, and such waste heat is now being looked for in the data sets from the WISE infrared telescope. So optical SETI could detect our strongest lasers on Earth, petawatt, 10 to the 15 watts, if it was 1,000 light years away. Radio SETI can detect our strongest transmitter on Earth, the Arecibo planetary radar, if it were 1,000 light years away. And within that 1,000 light years, there are about 1 million stars. For us to have a chance for there to be one technological civilization within those million stars, longevity of the civilization has to be 100,000 years or greater. We're looking to the future, to the large telescopes, JWST, looking for biosignatures, the large optical telescopes, the European ELT and the US TMT. And the TMT is not really that much smaller than the ELT. ELT is 39 meters, TMT is 30 meters. It's just that ELT advertised itself as being a life detection system. TMT hasn't. But I just found out last week that there's some spare space in the instrumentation plane, and maybe we can get an optical IR SETI detector on there. And in the radio, we look forward to the Square Kilometer Array, which certainly has a great heritage from the Allen telescope array designs. So, all right, suppose none of this ever works. Suppose we don't find a signal. I still think SETI is really, really, really worthwhile because it has this amazing effect of holding up a mirror, showing us ourselves from a cosmic perspective. And you know, in that mirror, we are all the same. And so it has the effect of trivializing the differences among Earthlings, differences that we're willing to spill blood over. We've got to get over that. I think SETI is a great way to do it. And so it's this idea of deep time and deep place and our position within it is something that astronomers and geologists and geophysicists can appreciate. They get to enjoy it every day. But it's something we actually have to spread. It's an idea. It's a meme. We should be spreading that meme across the planet. SETI should become a global endeavor. And then maybe we can figure out what the rest of that stardust has turned into. Thank you. Sure.
We have time for a couple of questions. If you have a question, please raise your hand. When you get the microphone, please stand up and ask your question.
Thank you for coming here today. My question is, some years ago, a couple of fellows you may have heard of, Brownlee and Ward, wrote a book called Rare Earth, in which they postulated that while intelligent life may be exceedingly rare in our galaxy, that microbial life might be comparatively ubiquitous. In light of that, has SETI ever considered changing its focus from the smart end of the scale down to the not so smart?
I'm actually very glad that you phrased it as the end of the scale, because my institution is called the SETI Institute. But we've got 75 scientists over there who are doing astrobiology. Right? So at SETI, we consider it all a continuum, looking for any kind of life, trying to understand the origins of life and its distribution. And so SETI is just one way. So I would say the SETI Institute has already embraced, from our beginning in 1984, that point of view. SETI as a discipline is just one end of that spectrum.
Hi, Jill.
Hello.
So I wanted to make a comment. You suggested that we need to be able to find civilizations that are 10 to the 5th years in longevity. Our civilization is what, 300 years, if we think about our technological civilization.
100 years.
Yeah, okay, even 100 years if you think about the real technologies. So we're orders of magnitude below the expectations, and this was all part of Drake's equations. This must be a little disheartening, especially in light of what, like Carl Sagan thought when we turned the telescopes to the sky, we were going to be finding lots and lots of stuff out there. I understand your final point that it's worth looking, but isn't it also worth turning inward and looking at what we can do at unifying ourselves around other topics that are so important?
I really hope, the point that I'm trying to make is I think SETI gives us an opportunity to do precisely that. Look, if we could globally get on board a SETI project, it's pretty benign, right? It isn't threatening. But it would be just one opportunity to get used to working with the others over there, as opposed to shooting them. So I think it's a sexy project. It's something that's easy to understand, and it could potentially build the base and the expectation for solving problems that don't stop at national boundaries, right? That are really global, and that we have to work on together. Let's get this one going. It's a no-brainer, right? It's easy. It's not threatening. If we can do this, we can do anything.
Good afternoon. Your talk was wonderful.
Thank you.
I'm an elementary school teacher, and I teach some kids in the junior level as well. And I'm trying to teach them. I'm very interested in what you're talking about, and I do try to teach them what SETI is looking for, which, of course, extraterrestrial life. And I noticed when you brought up the one image up there, it was about cells. And I'm wondering if you're ever looking at anything that isn't necessarily a compact cell, but still can reproduce, that tough definition of what's alive. Reproduce, take in energy, make more of itself. So do you ever look for anything that isn't necessarily just a, cellular life, let's say?
My astrobiology colleagues struggle mightily with the question of what is life. And they participated in and advised a National Academy study that was published maybe 3 or 4 years ago now on weird life, life that's other than life as we know it, life that uses different metabolic pathways, different biosolvents, wouldn't be discovered by any of the life-seeking instruments we've currently built because they all rely on DNA. So in some sense, yes, scientists at the SETI Institute are struggling with that, but they're struggling just as much as I am about how to do what you can't conceive. So what does it mean to look for some other kind of life that we don't know? How might you find it? Some work is being done. It's a really difficult question.
So please join me in thanking Dr. Jill Tarter.
Thank you.